Come on, let's attack exercise 1.1. Real numbers first chapter basics we completed in the previous video. Now we'll find out using Euclid Division lemma, which is very important for 1 mark. So you have 900 and 270. 270 is a small number. So now you have to divide 900 by using 270. So here when you look at, so this is very close to 300. 300 3 is a 900. So it can't divide more than 3 times. So 270 times 3 equal to 3 into 200 600, 3 into 70 equal to 210. So that is equal to 810. Now the remainder equal to 90 here, because 900 minus 810 equal to 90. Now the remainder is not equal to 0. So then what you have to do, you have to bring the previous divisor. So the divisor becomes dividend here. This is called continuation division. So 9 into 3. 9 3s are 27. We know very well. 90 into 3 equal to 270. So since the remainder equal to 0, so the procedure stops here. Then what you have to do, you have to write according to Euclid Division lemma format. What is Euclid Division lemma? So A is equal to BQ plus R. A is equal to BQ plus R, where so the remainder is always less than the divisor, which is B here, always greater than or equal to 0. So this is called Euclid Division lemma. Now let us try to write the steps in this format. So A is equal to here any number which is any integer which is 900. So 900 can be written as 270 into 3 plus what is the remainder? 90 is the remainder. Next 270 equal to, so 90 into 3 plus remainder is 0. So for what divisor remainder is 0? Always don't, actually you have to keep the star mark here, so that some of the children will keep 3 as the HCF, some of the children will write 270 as the HCF. So there is a lot of confusion. So what you have to do, better you keep the star mark here at the last divisor. So since 90 made the whole sum as a divisor 0, remainder 0, so therefore 90 is the HCF. So therefore the HCF of the given two numbers, which is 900 and 270, equal to 90. Okay. So don't forget, division also you can take. Actually some children will do the division in the rough column. So you can even show the same division also. So nothing will happen. Okay. Now the problem begins here. Why? Here we have only 196, and here the number is a very big number, which is a 5-digit number, 38,220. So here it is close to 200, it is close to 40,000. So what we have to do, we can estimate how many times actually 196 divides me. So 38,000 I am taking like this, 38,000 round figure. 196, okay, let me make a 200. 2 zeros cancel. So 2 19s equal to 38. So 196 divides 38,220, approximately 190 times plus. Okay. So now if you see, if you have to trial and error, 196 into 190. Okay. So 196 into, so the last number equal to 0 here. So 0 into 6 equal to 0. 196 if you multiply into 190, answer equal to, you will get 0 only, ending with 0 answer. Now if you try 191, but here 0, so not possible. 2. If you take 196 into 2 equal to 2 6 are 12, but here ending digit is 9. Like that, as you trial and error method, if you go up to 5 times, exactly it will divide. So what I am trying to say is, the number is around 40,000 or else 38,000. So this number is close to 200, round figure. So then like that you can estimate how many times 196 divides the given number. So now I am dividing it 38,220. Okay, you try children, because for last 10 years I have been teaching this 10th class, so that is why I am just doing go ahead directly. 196 times 195 equal to, that exactly gives you 38,220. So with one step only we reach the remainder 0. So give the star mark for the divisor. So this is the main answer of the given question. So therefore, now let us write the Euclid division lemma. A is equal to B cube plus R. So don't forget to write the condition. Remainder is always less than the divisor, which is called b, and greater than or equal to 0. Okay. Now by the way, a is actually, it's a dividend children, so which is any integer. B also integer only, so which is also called the divisor. Okay. So dividend equal to divisor into quotient plus remainder. Euclid division lemma, in fact, very close to the previous, almost equal to the previous division algorithm. Dividend equal to divisor into quotient plus remainder. Q you know very well. Q means a quotient only. R is actually remainder, not remaining. So here Q, Q and R are whole numbers anyway. Right. So now let us try to figure out the given division in this format. So what you have, A is equal to here, A is equal to this. So that is 38,220. Okay, equal to, very simple children, left into right plus down. Here also left into right plus down. Here 270 equal to left into right. That is 90 into 3 plus down number. So here 196 times 195 and then remainder 0. So that is equal to now HCF of so the given number 196 and 38,220 is equal to 196. So as I told you, so many times many children they calculate and they'll write 195 as a HCF. Don't confuse. Always the divisor will be the HCF. Okay, no? So better you keep the star mark. Similarly, let us go ahead with this. So now what kind of questions you can expect? This is 2022. So they may ask you 2022 and 2023. Find the HCF using Euclid Division lemma. So that's very simple. When you have two immediate numbers, always their difference is HCF. That is one only. But anyway, you will see here 1651, 2032. So now let us proceed. So as you know, this is the small number. Now write down here. So 2032, one time. So 1651. As you subtract here, 2 minus 1, 1. So 3 is not possible. So now you just take borrow here. This will become 19 and here 13. And then as you subtract here, 8 will be remaining here. Okay, so 9 minus 6 equal to 381. So now 381 is not a remainder, not a 0. Now you need to proceed here, 1651. So 3 times are 50, 3 5s are 15. Okay, so I mean 300 into 5 equal to 1500. So but actually we can't proceed 3 times. So let us try 381 into 3. Okay, so 3 1s are 3, 3 8s are 24, 2 carry, 3 3s are 9, 10, 11. 1143. Okay, fine. So let us try 381 into 4 times. 4 1s are 4, 4 8s are 32, 3 carry, 4 3s are 12 plus 15. So we can proceed up to 4 times. Okay, so as you multiply 1524. So now try to subtract and apply cancellation. Apply again, continue division. So we'll get the answer. Right. So as I told you previously, now we'll as you divide here 127. So since it is not a remainder, not a 0, so now bring the 381 here. Dividend will become divisor. So 3 times that is equal to 381. So remainder equal to 0. So chalo. Now Euclid division lemma equal to A is equal to BQ plus R, where remainder is always less than the divisor but greater than or equal to 0. So therefore let us write 2032. So try to left into right plus down. That is the divisor into quotient plus the remainder 381. Similarly 1651 you can write it as left number, that is divisor into quotient plus remainder 127. So again you have to proceed. 381 equal to divisor into quotient plus remainder 127 times 3 plus remainder 0. Since the remainder is 0 because of 127 divisor, so therefore the HCF of the given number is equal to 127. Okay, this is how we'll do. So the HCF of do this, you will be having few questions like 300 and 550. So 97, 108. So these numbers will come for 1 mark questions. So don't neglect. Be strong, be perfect. So you can do it. Okay, children. Now let us continue the very important part of the chapter. So the number pattern. Show that the given positive integer or positive integer is of the form so and so, so and so. So such questions we'll see now. Right. So use Euclid Division lemma. So means you have to prove the given question, given number pattern. So using Euclid Division lemma. Okay. So use Euclid Division lemma to show that any positive odd integer. Okay. So try to understand the keywords of the odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5. So now let us do some background work here. So here when you see 6q plus 1, 6q plus 3, 6q plus 5, okay, so here suppose q is equal to 0, let us say 6 plus 1 equal to 7, odd number, 6 plus 3 equal to 9, odd number, so 6 plus 5 equal to 11, again odd number. So generally any odd number in the world, say for example, if you take so 31, let us say 31, you can write as 6 into something plus how much? 6 5 is 30 plus 1. So where here 5 equal to q, so 6q plus 1. So otherwise 9 is there. 9, how can you write? 6 into 1 plus 3. Again, which is coming any one of the format, that is 6q plus 3 only. So like this in the world, if you take any one number, any odd number, not one number, so odd number, odd, positive odd integer, so that always any one of these three formats only will be. That is the main intention. Okay. Now let us try to observe the given question, compare the given question with Euclid Division lemma. So it means this is any number can be written as 6q plus 1. Now a is equal to bq plus r. So when you see here b is equal to 6. So from the given, what we can write from the given, okay, from the given, so b is equal to 6, okay, and as you know the condition Euclid Division lemma, what is the condition? R should be less than the b divisor. R is less than, divisor is what? 6 is the divisor, what is the divisor here? 6 is the divisor, so less than 0. So therefore R values are less than 6, not less than 0, 6. So 0, 1, 2, 3, 4, 5. Okay, proceed up to 6, strike out 6 because less than 6 now. So the remainders will be 0, 1, 2, 3, 4, 5. That's it. Now nothing is there. So you have to substitute these values in Euclid Division lemma. So Euclid Division lemma, some teachers will teach, so they will write a table and they will substitute the numbers 1, 2, 3, 4. So I think better you don't do like that. So always better you write as a best way. That is how we are going to do here. Euclid Division lemma A is equal to bq plus r. So where remainder is less than b, greater than or equal to 0. So now you can apply one cloud also, you can box also. Now let us see all the cases. Substitute b comma r values in Euclid Division lemma. Okay. So what we have done till now? First we have identified the divisor b, and after that we have written the remainders less than 6. So b we have identified, r we have identified, b we got it from the given format. Always you have to get the b value from the given format only. Okay. So now after that we have written the Euclid Division lemma formula, and we are substituting r value, b value in this. So where r is equal to 0, b is equal to 6. So we will get a is equal to 6q plus 0. Now see here, some of the children, suppose you show that 6m plus 1, odd integer 6m plus 1, 6m plus 3, they will directly write here 6m plus 0. That is not correct. Always wrong. You have to write first in the formats of q terms. After later on, so further simplification you can decide it. Now r is equal to 1, b is equal to 6. B will not change, remainders will change. A is equal to 6q plus 1. Similarly, r is equal to 2, same b is equal to 6. A a is equal to 6 cube plus 2. Similarly, as you keep on writing here, I am writing directly 6 cube plus 3. A is equal to 6 cube plus 4 and a is equal to 6 cube plus 5. So done. Okay, all the cases r is equal to 3, r is equal to 4, r is equal to 5. Now if you observe, q is equal to any positive integer. Okay, so 6 into 1, 6. 6 plus 0 equal to 6 only, which is odd even number, but we want odd number. So I am taking 6 2s are 12. 12 plus 0 again even number. So now let us substitute all the values by taking in place of 6 1 only. 6 1s are 6 plus 0, 6 even number. 6 1s are 6 plus 1, 7. So odd number. 6 plus 2, 8 even number. 6 plus 3 odd number. 6 plus 4, 10 even number. 6 plus 5 odd number. So it is so much clear. The alternative numbers what you have here, so they are odd numbers. What are the odd numbers here? 6 cube plus 1 plus 3 plus 5. So therefore from this observation what we can write, therefore any positive integer, any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5. Okay, so you have made a conclusion. Before that you can make one contradictory statement, right? What is that? So so it is very much clear. It is clear that any positive even integer is of the form 6 cube plus 0, 6 cube plus 2, 6 cube plus 4. So if these numbers are even numbers, even integers, so rest of all are not even only, not even nothing but odd only. Remaining means 6 cube plus 1 plus 3 plus 5. So you can make a statement, even you can modify. So it is for any some positive integer, for any positive integer, we get 6 cube plus 0, 6 cube plus 2, 6 cube plus 4 as even numbers. So that statement also you can write here. So since these three are even numbers, remaining three are definitely odd numbers only. So like that you can write. So once again, B value we have written from the given question, Q remainders less than 6. After that we have written Euclid Division lemma and we have substituted B value, R value. So we will get plus 6 cube plus 0 plus 1 plus 2 plus 3 plus 4 plus 5. After that we substitute in place of Q any number, any positive integer you can substitute. Example, if you substitute 5, 6 5s are 30, even number. 6 5s are 30 plus 1, 31, odd number. 30 plus 2, even number. 30 plus 3, odd number. 30 plus 4, even number. 30 plus 5, odd number. So we want odd number and we have to show that only. So therefore the any positive integer is of the form, so plus 1 plus 3 plus 5. Done, children. Similarly we are going to have question number 3. So that is asked many number of times. So that is very important. Question number 3. So show that the square of any positive integer is of the form 3p or 3p plus 1. Interestingly, the second question is just without any square, any cube. The third question is a square of any positive integer. Fourth question is a cube of any positive integer. Will be it will be 9m plus 1 and 9m plus 3, 9m and 9m plus 1. 9m plus 3, 8. So that question is there. Those two questions we'll see. So this is a very important question. So sometimes the numbers will be changed. So nothing is there actually. So now let us see the background here. So what you mean to say is 2 square is 4. Square of any positive integer. 3 square equal to 9. 4 square equal to 16. 5 square equal to 25. So these numbers you can write any one of these two formats. What is that? Either 3p or 3p plus 1. Now let us take 4. 4 can be written as 3 into 1. 3 1s are 3 plus 1. So if you take 9, 9 can be written as 3 into 3. So it is looking like 3p. It is looking like 3p plus 1. So similarly 16 is there. So 3 into 5, 15 plus 1. Again this is in the format 3p plus 1. So like that we are studying the number patterns. So show that the square of using Euclid division lemma. Okay, don't forget. So now let us write the b value. As you compare b is equal to 3, remainders are 0, 1, 2. So as you know, less than 3. So now let us write Euclid division lemma. Very, very important, children. A is equal to bq plus r less than b, or greater than or equal to 0. So now let us substitute here. So b is equal to 3, r is equal to 0. So therefore a is equal to bq plus 0, and r is equal to 1, a is equal to bq plus 1. Okay, similarly r is equal to 2, so a is equal to bq plus 2. So now we have three situations, three numbers are possible. So now I am taking a is equal to bq. So squaring on both sides, don't write SOP, so you have to write full form. So applying a square, 0 you can neglect it. So bq, b value is how much? R is equal to, children. So 3q, okay, 3q, so 3q plus 2. So a is equal to 3q plus 0, so which is 3q. So apply squaring on both sides, that is equal to 9q square. So 9, as you take 3 common, you will get 3q square, where so you can write as 3p, where p is equal to 3q square for some positive integer. Similarly, let us take the second case, that is 3q plus 1. Third case, 3q plus 2. We have to apply squaring on both sides. Now I am doing that. Now I have explained here, I have taken case 2, that means second number. A is equal to 3q plus 1 whole square. So I have expanded a plus b whole square because it is a binomial. So 3q square equal to 9q square. 2 3 is 6q plus 1. 1 square equal to 1. Now you have to take 3 common here. So 3q square, 3 2 is 6q, and the plus 1 will not come. So as a common. Now you can consider this total bracket part as p, where p is equal to 3q square plus 2q for some positive integer values. So which is equal to 3p plus 1. Similarly, we will do that also. Right. So as you see here, so a square equal to 3q plus 2 whole square, the last number, a square plus 2ab plus b square, that is equal to 9q square. 2 3 is 6, 6 2 is 12, 12q plus 2 2 is 4. So 9q square plus 12q plus 4 you can write as 3 plus 1. Now for all the three terms you can take 3 common. So as you take 3 common, 3q square plus 3 4 is 12q, 3 1 is 3, and plus 1. This total bracket you can write as p. So 3p plus 1, where p is equal to this total bracket whatever you have. So that is equal to 3p plus 1. What you have seen, when you squared you got 3q plus 1. When you squared the second number, again you got 3p plus 1, and the first number you got 3p. So therefore what we can consider from above all, therefore the square of any positive or odd integer, the square of any positive integer is of the form 3p or 3p plus 1 for some positive integer values. This is how we will do it. It's a very, very important. So please do till you understand. You practice only this question only. Later on you can do cubing and the general numbers. Even they will change the formats. Other than 3p plus 1, they'll keep 3m plus 1, like that also they will give. Okay, don't get confused. All the best. We'll continue remaining part in the next video. Till then, bye. Take care.